2. Charged tape revisited. In the previous lab, we modeled two positively charged U-tapes as a single point charge and used formulas to determine the amount of charge on each tape. This method has some inaccuracies since it assumes the charge on each tape is concentrated in the center. Using computational methods, in this lab we will model each tape as multiple point charges and calculate the electric force between each of the charges, and we can then use this model to calculate a more accurate value of the charge on each U-tape. In this lab, the charge on the U-tape was determined to be 10.9 nanocoulombs, which is more than the previous approximation of 7.5. Each tape was modeled as 10-point charges spaced evenly across the horizontal axis. The total charge of the tape was assumed to be evenly distributed between all charges, and the electric forces acting on each point charge were calculated. The suspended tape was assumed to be a point mass and a single gravitational force was simulated. The electrical forces between the charges on the same tape and on the bottom tapes and the gravitational forces were ignored. In Lab 1, a U-tape was suspended between two insulating boxes and the second tape was used to levitate the first tape, and the values at that point were measured. That data from Lab 1 was reused with the measured values and physical constants given on the right. Key values include the mass of the U-tape at 1.16 grams and the separation distance of 1.8 centimeters. In the code, we use two nested for loops to determine the total electric force on the top tape. First, the forces from each of the bottom charges on one of the top charges is calculated. Then, this process is iterated for all of the top charges, with the vector force on each charge being added to the total force. The charge on the U-tape was varied between simulations until it exactly equaled the gravitational force on the tape. After running the simulation with varying values for the charge on each U-tape was determined to be approximately 1.09 times 10 to the negative 8th coulombs, or 10.9 nanocoulombs. This is a larger value than the estimate from Lab 1, and this result makes sense since the horizontal components of the forces acting on the top tape are essentially wasted, and so the charge required to levitate the tape will be greater. This model is not without flaws, and some potential sources for error include the neglected air resistance of currents in the room, which could cause the suspended tape to move. Improper preparation and handling of the tapes can also cause them to have different charges. Inaccurate measurements of the mass and separation distance of the U-tapes could also create discrepancies. If each U-tape was modeled as a single point charge instead of multiple distributed charges, as was done in Lab 1, the calculated value for the charge on each tape would be approximately 7.5 nanocoulombs. This is significantly less than the value of 10.9 nanocoulombs determined in Lab 2. These values vary because when modeling distributed charges, a portion of the electric force between two non-opposing charges, for example those located diagonally from each other, will be in the horizontal direction. By the symmetry principle, the horizontal forces on the top tape cancel out. As a result, a greater charge is needed to create enough electric force in the vertical direction to oppose the force of gravity and levitate the tape. The value determined in Lab 2 is likely closer to the actual value of the charge on each U-tape. This is because it is a closer approximation of a charge that is evenly distributed throughout the tape and more accurately accounts for the wasted horizontal forces present in the system of tapes. Thank you.